I started the recording because we will be saving the webinars for further reference. Okay, I think 5 minutes have passed and we can already start. So I will invite Amit, who recently started working with us. So I would you I will let you introduce yourself and proceed with the presentation.
Sure. Thanks, Nikolai. And I'll quickly share my screen. That's okay. Is my screen visible?
Yes.
Okay, great. So, hello everyone. I'm Amit. I'm a pediatric and oncoradiologist from New Delhi, India. And basically, my goal for today's, next 10 to 15 minutes is basically to give you an insight into the applications of all these brain tumor segmentations, especially from a radiologist perspective. So I'm pretty sure that by now you know what a segmentation mask is. It's basically we are trying to delineate all of the voxels where the tumor is present and create a digital segmentation mask, right? But so what I'm going to talk about is, so once we have that digital segmentation volumetric mask, what all can we do with that mask and what all is possible, especially from a radiologist perspective. So let's get started straight away. Uh, just a second. Okay. So I've tried to divide it into, something that can be done directly in the clinic and something that is more of a research and academic problems. So let's start with the clinical applications of these segmentation masks. So as radiologists, our job is much more than just detecting a brain tumor or for that matter, any tumor. We have to, measure the tumor. We have to describe the tumor characteristics and describe its extent, what all structure it's involving. We have to follow up the tumor on different scans as the patient undergoes treatment, and we have to communicate our findings and the tumor extent to the treating, say, oncologist or neurosurgeon. And as this medical imaging and as medicine as a science progresses, a radiologist is expected to do this in a more quantitative and an objective manner. And I think this is where the segmentation algorithms, the automated segmentation algorithms can be really helpful to us. So I think to start with, the most obvious clinical application of these tumor segmentations is basically tumor measurement. And so basically how we do it traditionally is basically measure the largest diameter of a tumor, or at the max measure the two perpendicular largest diameters of a tumor. So that's how radiologists do it manually even today. That's how we report a tumor measurement today. But what the inherent problem with this measurement is that brain tumors, or for that matter any tumors, they are rarely, nice spherical shape. They are actually very irregular and in different planes. So if we look at this image, this is from the transverse section, this one is sagittal, and this one is coronal section. And as you can see, the tumor can extend irregularly in different planes, and it can have different largest diameters in different planes, and that adds an inherent subjectivity to all of these measurements. And as you can imagine, different radiologists can, tend to measure different diameters for the tumor, and this becomes a problem when we try to objectively quantify the tumor burden as well as follow up the tumors for further after patient's treatment and follow up the tumor. So an accurate segmentation algorithm that is able to, delineate the entire tumor volume gives us a much more objective and reproducible measure of the tumor burden as compared to what we do today manually. And the volumetric measurement is simply just not possible manually, to do, because it's just too much time intensive right now. So after tumor measurement, another very important application is baseline mapping. So if you look at this patient, especially in patients with such tumors, where you can see at least 20, 30 tumors, brain metastasis involving the entire brain, it's it's hard, if not impossible, to actually delineate to each lesion, actually delineate each lesion as well as describe each lesion and its extent. And herein, an automated segmentation algorithm can really help us as radiologists and as clinicians to actually quantify the tumor burden in a much more objective manner. And this can provide a much reproducible mapping on the baseline scan, and then help us to follow up the patient in an objective manner, as compared to what we do today. What we do today is more of a qualitative description of all these multiple lesions in the brain, and we tend to quantify and measure the largest tumors, and we do not, where it's not just not possible to measure each and every lesion in such patients. And that's where I think automated segmentation can be very helpful. Similar application is follow-up of tumor components. So when a patient is undergoing some treatment, say radiation therapy, or post-operative, patient has undergone brain surgery for tumor, on imaging, we are trying to answer a very simple question. Is the lesion stable? Is the lesion progressing, or is it becoming better with treatment? But this simple question is actually, sometimes it becomes very difficult to answer, simply because the different tumor components can change in unpredictable manners with treatment. For example, the enhancing tumor component may increase or decrease. The necrotic component may again increase or decrease, as well as the edema, brain edema associated with the lesion can also change differentially. And this is an image from the BraTS data only. Here, as you will see, that the segmentation masks are there for separate tumor components, including the enhancing tumor component, the necrotic part, as well as for the edema. So such segmentations can help us to objectively follow up different tumor components across the patient's timeline, and give a more measurable quantification of the change in the tumor components over time. And so another application which is especially relevant for, so this is for radiotherapy, radiation oncologists, and for neurosurgeons. This is for exact treatment planning, and exact delineation of the tumor can help the radiotherapist to plan the field of view for radiation, so as to focus the radiation on the tumor as compared to the rest of the brain parenchyma. And similarly, for neurosurgeons, it gives them an exact idea of the tumor extent, as well as the involvement of the structures outside the tumor and in the surrounding brain, what all structures are involved, and what they can expect when they go in and try to reset this tumor out in the surgery. So these were basically the direct clinical application, which you can just imagine. Once we have a direct a volumetric segmentation of a tumor, it can be used directly for all these clinical applications. But these segmentations can have a lot of multiple downstream analysis, which are very much important in research and academia. And I think the most prominent example of it is radiomics. So once we have a volumetric tumor delineation, we can use that tumor volume, to extract thousands of radiomic features or even deep features from all these algorithms, and try to correlate these features with the survival prediction for the patient. And as I said, as the medicine progresses, there is more and more emphasis on genetic associations with all these tumors, and this radiomic analysis can help us to correlate these tumors with the genetic analysis and the molecular associations associated with these tumors. As I previously said, these volumetric measurements can be more objective as compared to what we do manually, and this can help us in the clinical trials and provide a more objective measure of the tumor response. Similarly, the BraTS dataset itself has been used specifically for to give a fair comparison with all of these segmentation algorithms and benchmarking AI models. And similarly, if we can segment all these tumor components very well in the different enhancing tumor component or the necrotic component, this can also be a very good teaching material for the radiology trainees who are trying to learn neuro-oncology applications. So basically, this is all I have to talk about. And it's I would say the message is that this segmentation is just not delineating the tumor. I think there are a lot of downstream real applications of these segmentations once we have a good segmentation and an accurate segmentation algorithm. And this can really change how we quantify tumors and how we follow up these tumors in a patient's journey. Thanks. Yeah, Nikolai.
Thank you, Amit. I have a question. So are you using automated segmentation models in your clinical practice?
So I would say not for brain tumors right now, because as I see it, this is still a very high stakes application of AI, which will need a lot of, an accurate algorithm to start with and a lot of clinical validation itself. But once we have it, it's a very great ambition to have, and it's an ambition that we are all working towards, but not right now in the clinics. We have some AI applications like on chest radiographs, which are much more developed, and I would say they are low stakes as compared to a brain tumor segmentation. Especially, so another application for radiotherapy, so they are using automated segmentations for radiotherapy planning, which are later edited by the radiation oncologist before they plan the treatment. That's one that is already there, but not for, I would say, something like radiomic or survival analysis or prediction of treatment response, nothing like that. Yeah.
I see. I see. And um have you encountered some issues or um some problems with the integration of the models that are currently being used? Like, is it
Yeah.
annoying in a
Mhm.
way, or is it
No.
smooth to use such tools?
I wish it was, I could say that it has been a pleasure integrating AI into our workflow. It's a pain and it's so frustrating when you know that. So we have another liver segmentation algorithm, which is pretty easy, right? Just to segment the liver, we have to have liver volumes in some patients who are supposed to undergo liver surgery. So that's a very manually time taking task. So we have a segmentation algorithm which does fine, but just to get it into packs, it's not been possible. So right now we are using that the segmentation algorithm separately from our packs. It's because it's just not getting integrated into our packs. So it's been a pain, and I know there are some local factors associated with it, but I can't imagine that anywhere integrating any AI into packs anywhere has been a good experience for radiologists, as far as I know.
I understand. I
Yeah.
understand. Then maybe, who knows, maybe in a couple of years this could be a success story.
Yeah. I wish, I hope so.
Okay, great.
Yeah.
Well, thank you, Amit, for introducing us to the clinical aspect of what we're doing. And without further ado, I will proceed
Yeah.
to the next steps. So let me just share my screen. Okay, just a second. Okay, so you should see, like, do you see, would you please guide me on what are
Yes.
you seeing right now? Is it the slide or the presenter mode or the PowerPoint?
Yes, we can see the slides, the overview of the strategy for the next 2 weeks.
Yeah, same thing.
Okay, great. So is it like full screen?
Yeah.
Okay,
Yeah,
great. And
Yeah, full screen.
okay, great. And do the slides move here?
Yeah.
Okay, great. So this is the overview of the strategy for the next 2 weeks. We already brushed upon the software that you would need to visualize the data. We'll be using it along the way to check our data and to see if everything's okay with the algorithm and everything. So we'll be dealing with ITK Snap and 3D Slicer again. So we also have a separate lecture that is purely medical on the different characteristics of brain tumor imaging on MRI. And so just excuse me for a second. I'm hearing myself as a Nico, so if someone hasn't turned muted their microphone, I would ask you to do so. Okay, and today we will also understand why we need pre-processing of the raw MRI data. We'll set up the basic environment and download the basic tools that we need to do anything related to coding and training algorithms. Tomorrow we will continue with, we'll wrap up the data pre-processing, and we'll understand how we should prepare the data and organize it in order to feed it in a segmentation algorithm. And from there on, we will go over different training pipelines. And we will also, next week, we'll be giving you the Rumpot codes, and we'll conduct a session on how to use them and which options from Rumpot should you choose based on your needs. And the week after, we wrap up the model training, and we'll write up the short paper. We'll dockerize our algorithm, and by 20th or 23rd of July, we'll submit to the BraTS challenge. So this is a short overview of what awaits us. So let us dive deep into why we need pre-processing of raw MRI data. So measurements across multiple sites introduces unwanted technical variability in the images, and this could distort downstream measurements, assessing volumes, etc. So this is called the scanner effect. So in different institutions, they're using different scanners, different parameters, etc. Also, differences in the MRI studies could be observed even within one institution and for one patient. So this is called intensity unit effect. And those two are the reason why we might observe that the intensity of a voxel on one MRI study might represent a completely different tissue intensity on another MRI study. And what is the solution? We need to pre-process the data so that it comes in a standardized way for the brain tumor segmentation model to train itself. And what's the solution? Intensity normalization techniques. And we'll be diving deeper in those tomorrow. But this is it's important for you to know that this is a crucial step in the pre-processing of MRI data. And even though training an algorithm on already pre-processed and scale stripped data provided by the BRAT challenge is not needed, you still have to understand what were the steps that this data underwent, and it will help you understand what you see and how the brain tumor segmentation algorithm is being trained. Like, what is the data that it requires to be properly trained? What is another issue that we have with the raw MRI data? They're not anonymized. The face and the skull can be reconstructed, as you can see on this figure, and this way the patient's face could be identified. So in order to comply with the Health Insurance Portability and Accountability Act, many just go with HIPAA. So probably this is the last time you hear it the way I said it. Most of clinicians and researchers call it HIPAA and the GDPR. So what is the solution to this problem? The solution is to skill strip the data beforehand so that the patient cannot be identified, and the MRI data, the brain tissue that we need for our brain tumor segmentation models, could be shared in an open source manner, and it could be shared to the research community without we having to worry whether it complies with HIPAA and GDPR. So this is a basic requirement of any open source data to be de-anonymized. So without further ado, I will go straight to what we need to start training our algorithm. The first and foremost is downloading and installing Python. I will just, so would you please unmute your microphones and tell me how many of you have already installed Python? Like, are there people of you who are gonna undergo this step for the first time?
I have Python installed in my laptop.
Okay, so it's one person. Okay.
Yeah, me too. I do have Python installed in my laptop too.
Okay, so we have two. Someone else?
Yeah, the same for. Yeah.
Okay, great. So like it's more like 50-50. We'll go over installing the Python after we finish with this PowerPoint. So the next step would be to download PowerShell for Windows. It's a useful tool. Like, you can use command prompt, but PowerShell also comes in handy, where you can use it as basically as the same as a command prompt, where you can install Python or check the latest version of Python that you have on your computer. Just here are some commands which you can call in the PowerShell just to check whether everything with your Python is okay on your computer. So there are plenty of options in terms of software and cloud services where you can type code and where you can train your algorithm. Here I have given you an example of where we will be, where we as a team will be doing our coding and model training. So this is Visual Studio Code. It's available for Windows and for Mac as well. And it is the go-to software for building medical image segmentation models. It gives you all the functionality, and it's light on your machine. You can directly open Python notebooks, create plots, visualize data. It's a multimodal platform where you can do a lot of computational stuff. I'd like to show some alternative options. Like, if you don't like VS Code, you can use Anaconda. It's as you can see here, it it allows you to install Python, Jupyter, and thousands of data science packages. So what are the drawbacks? It's heavy on your machine. I have tried it out, and from my personal experience, for the purposes of BraTS, I prefer VS Code. But if you like to use an account, you can do it as well. And yeah, one additional option that I haven't put here on a slide is using Google Colab. I guess all of you are aware of that. The thing is that it's a cloud-based, and it's if you want for it to work with offline files, you have to do some additional steps. And again, from my personal experience, I believe that sticking with VS Code will be good enough for the purposes of the challenge. So why do we need all of that? We understood why we need to pre-process the data. Like the BRAS data set is already it's ready to be fed into the training algorithm, but you have to know what it has underwent. And in order to do any computational pre-processing, of course, you need an environment and also Python. A lot of tools come as a Python code on GitHub. So this is why we will install Python and VS Code. And the third step is to actually understand what's the format of the raw MRI data. It comes in DICOM. This is the digital imaging and communications in medicine format. So this is the format in which all the medical imaging files are stored and shared. So like if you get some raw data from an institution and you want to train an algorithm on it, you first have to convert it to Nifty so that you can pre-process it appropriately, so that you can skill strip it, and then work with the Nifty files. And there are several tools that you can use to convert DICOM to Nifty. I'll be showing you a tool that I have used, and I'll show you from where you can download it. But this is just purely for educational purposes. You can use different tools. I'll be after the session. You get all the links and additional resources. So yeah, and the last step before we can convert DICOM files to Nifty files would be to recognize how different MRI sequences look like. Because when you get the raw data, maybe the folders that can comprise the DICOM files are named with just some random numbers, and you have to open those files using DICOM and to check whether this is T1, T2, flare, or T1 plus contrast. These are the four main sequences used in brain tumor segmentation algorithm training. So yeah, this was the plan for today. The meeting won't stretch as much as it did the last time, so don't worry about it. We will be sticking with shorter sessions, but more frequent ones. So I might have brushed upon some topics that we won't go over today, but we'll continue with them tomorrow. So yeah, I'll just let me stop sharing for a second before we go over all the steps that I mentioned. So before that, do you have any questions so far? Like, is there information from the one that I presented that you hear for the first time? Like, is there something that you have no idea what it is, so that we can focus more on that? what are your preferences? Okay, I guess there are no questions as of now. So before we continue, I'd like to type something in the chat, and I would like you to tell me whether you have access to the chat. If it doesn't work, I will just use the WhatsApp group. Okay, great. So the first step would be to download Python. Whoever hasn't downloaded it, let me just share the link to it. It takes only a couple of minutes. You should open the web page and share my screen again. Yeah, so the link that I shared is specifically for the releases that are for Windows. Is someone of you using Mac? Like, how many of you are using Microsoft Windows?
Oh, well, for me, I'm using Mac, so.
Okay, yeah, but you have already installed Python, right? I don't have to send a separate.
Yeah, I do have Python, I do have VS Code, I do have all these.
Okay, great.
I'm also using Mac as well.
Okay, great. And you're the second person who has already installed Python, so I won't send any additional links. What you have to do is to just click on one of the latest releases, save it as an application, save, and then go to where it is saved and click 2 times on it. And because I have already installed it, it doesn't give me the option to install. So I'll just click repair. If you haven't installed it, you just click install. And it should take only a couple of minutes for the process to be ready. So in the meantime, I'll ask the people who are downloading it now, have you downloaded? Have you managed to reach this website and download it? Have you managed to download the package? Oh, it takes some time. So I just will proceed with the next step. I hope everything is clear for now. So yeah, this was the first step, to download the package, and the next step is to open Windows PowerShell that I showed you earlier. So this is just a sanity check to check whether everything is working well with your Python package. it's not required to do so. It's not required to open Windows PowerShell or to do any of that. It's just one step of the whole process that I think it's good for me to show you. So let's give me a second. So I'll be sending a second link. So this link contains information on how to set up your Python environment and how to check whether everything is working fine. So leave the link in the chat. And I'm leaving this link here because from this web page you can copy this line. You can copy it from here. Go to PowerShell and paste it. So this is going to be the sanity check whether you have Python installed on your machine. So as you can see, I have installed the version that I shown you, and everything should be working perfectly fine. Good. So we have installed Python. We know that everything's working fine with it. What is the next step? To install VS Studio. VS Studio, this is abbreviation of Visual Studio Code. As I said, it's the software that I prefer for using code because it gives you the functionality and it's really easy on your machine. So I have already downloaded it and installed it. There is nothing special about it. You just download, click the exe file, and just install it on your machine. I'll just leave the link. You're not getting the links. Okay, I'll be sending. I'll click quickly go to WhatsApp and send the links there. If you don't see them on the chat. So the order in which I'm sending the links matches the steps that we need to do so. You can start from top and go one by one. Okay, great. So I have already installed VS Code as I said. So I'll just open it, the software. And this is the initial page. So in order to start a project, start a Jupyter notebook, what we need to do is to first create the folder where we need this project to be. So I'll just go to my file explorer. I'll just open my file explorer, and depending on your personal preferences, I'll just create a folder where I want my project to be. So I'll just create a new folder, go with practice. and we're good to go. So I have already created an empty folder, and I get back to the VS Code, and I click on Open Folder. I go to the directory of the folder that I just created. It's called Practice. I select it, and voila! Now I am working in the practice folder. So before starting to type code or to train an algorithm, I need to create a virtual environment. And why do I need to do that? So when you start a project, you want to create a virtual environment so that the codes and the packages don't interfere with other virtual environments and projects, so that it is all here. So as you saw, what I did, I just put the terminal here, and what I want to type is Python dash m venv interval dot venv. So this is, by using this command in the terminal, I'll create a virtual environment within the practice folder. Good. So now we already have the virtual environment here, as you can see. And what I want to do, click the right button of my mouse and create a new file. It is important, so you can name your file the way you want. So I'll just, for consistency, I'll just name it practice, and I'll type dot N I P Y N B. So this is why you should type that, because you want the file extension to tell your computer that this is a Python notebook. I click enter, and we have the notebook here. So this is where we will be typing code and pasting code. And if you ever, just not only for the purposes of training algorithms, but for every other purpose in which you might need to type down code, this is very beneficial to just know how to basically set up an environment. So before we start typing any type of code, we need to select kernel. Click here. When you click here, it directly gets you to the top of the page, and you should click Python environments. And since I have already installed Python, it pops up here, and I just click it. So now I am working in my virtual environment. I have created a notebook file, and I have selected the kernel, and now I can click code, and there we go. Now you can type whatever you want. You can use AI agents, etc. So yeah, this is the most basic setting up an environment that you would need. One issue that you might encounter while doing that is to not have when you click select kernel, the Python doesn't pop up here. And how you can fix that is to go to extensions. It's right here. And here I can see all my installed extensions. And one issue that I have encountered was that my Python extension was disabled. So you can easily click on your extension, and here if it's disabled, you can click enable so that it is recognized by VS Code, and so that you can select your kernel and start typing the code that you need. So yeah, this was I won't be, so for the ones of you who already have coding experience, this was very basic, and I know that you have experience with many more languages and packages and etc. But for those who are still in the beginning, I would like to just stop here and to give you time to just go to just complete these basic steps and know that you can set up the most basic environment for any future projects and codes and etc. So I have sent all the links in the WhatsApp group, so you can go over the steps. I'll give you time to go over the steps after we complete the presentation, because some of I want to first go over everything, and then I'll be available for future assistance after the after we have after we have completed the whole after we have underwent over all the material for today. So don't worry if you have questions. I'll be in the meeting after, so that you can ask your questions, and so that we can go over together if you need to. So let me proceed with the next steps. So the next step would be for you to understand how what DICOM is and how to open DICOM files, and in what form the raw data comes. So before that, I'll share in the WhatsApp group the link to Radiant. Share my screen again. So Radiant is very well-known software used by radiologists and researchers, software for visualizing DICOM images. It is usually paid, usually all the institutions pay license, and then so that they can use it in their daily practice. I haven't paid a license because I don't usually use Radiant home. I use Radiant where I work. But the good thing is that you can download it and still use it as a free trial. So yeah, I send the link to this page in the WhatsApp group, where you can download Radiant so that you can learn how to visualize raw MRI data. And let me proceed with introducing you to how raw MRI data comes. So this is a data set that we recently got, and we'll be adding this non-annotated data to the BraTS data set so that we can foster and motivate people to use semi-supervised approaches. For you that are not aware of what semi-supervised training is, so fully supervised training is feeding an algorithm with all the MRI images with their corresponding ground truth annotations of the lesions. You already know what annotation is. But semi-supervised training is a way for a way to overcome the fact that obtaining annotated data is from institutions is usually really hard. There is not enough data that comes with high quality annotations to feed good generalizable algorithms that are ready to be deployed to clinical practice. So one alternative is to use semi-supervised training, which is feeding, getting additional non-annotated data and train an algorithm on the annotated portion of the data set, then create predictions on the non-annotated portion of the data set, and then retrain the algorithm. We won't be getting deeper into that today. It was just a short introduction on why we need non-annotated data and why we are fostering semi-supervised training in this edition of the Brain Tumor Segmentation Challenge. So let me open a sample case. So every folder contains one MRI study. And when I open the study, I proceed opening all the subfolders until I get to those 4 folders. And you have to figure out what these 4 folders contain. So if I open a folder, I see that these are already the DICOM images. These are the slices. So this folder containing all the slices comprises one MRI sequence, and these are all the 4 sequences used in this that are available for this data set. So in order to convert those DICOM files to Nifty files, you have to know which is the sequence of each of those folder, which is the MRI sequence in which these DICOM images were obtained. So in order to do that, you have to visualize every single folder. So what I do, I click, I'll be sending you a link to, since this will be open source. So yeah, I cannot share any data that is not SQL stripped because the only data that I can share is only SQL stripped anonymized data. So this is why I'll be just showing you how to recognize the sequences and how the data looks, how the raw data looks. So I'll click the right button and open this folder with Radiant. So I have to wait 15 minutes because 15 seconds because, as I said, this is a non-paid version. I don't have an institutional license to use back home. Okay, great. So this is a sample of, this is one sequence. As you know, maybe some of you don't know, but in order, one MRI study comprises several sequences, and every sequence is obtained separately. Like this scan was obtained separately from the other sequences that you see here. Like this is one sequence, this is second, third, and fourth, and yada yada. So in order to recognize what sequence this is, like for me and for the radiologist, it's pretty easy. You just recognize what the sequence is. But I'll give you, like, there are plenty of signs and plenty of methods that you can use to recognize what's the sequence that you're looking at. But I'll just keep it short and simple. So, as you know, the brain has gray matter and white matter. So the gray matter is very rich in cell bodies, and the white matter comprises the axons of those neurons that reside in the gray matter in the cortex, and the axons are um, surrounded by myelin, which helps conduct the signals. And yes, this is the main difference between the gray matter and the white matter. And how you can recognize what sequence this is. So this is T1 weighted imaging. Many people call the T1 the anatomic depiction of the brain because the gray matter looks gray and the white matter looks white. So in the terms that are used when describing an MRI image and the intensity of certain areas or lesions is hyperintensity, isointensity, or hypointensity. So if someone is brighter, it is hyperintense. If something is darker, it's hypointense. And if something matches the intensity of the brain parenchyma, it's called isointense. So as you can see here, the gray matter is gray, the white matter is white. So this is what gets us to the conclusion that this is T1 weighted imaging. But in addition to that, you need to know whether this is contrast enhanced or not. So what is contrast? So the contrast is injected in the person blood flow, and it goes to every part of the body, including the brain. And here you can see that usually the contrast on T1 weighted imaging is hyper intense, so it's white. So here you can see the vessels very well defined and hyper intense. So this is why they carry contrast, gadolinium contrast. So ergo, this is T1 contrast enhanced sequence. Is everything clear so far? So you have the anatomical image of the brain, and also you can clearly see the vessels which carry the contrast. And if you scroll here, we can see a lesion. It's contrast enhancing lesion. So this is the contrast enhancing portion of the lesion. And it is hyper intense because it has taken up the contrast. So these are the main ways we can orient whether this is T1 post contrast or not. So I'll just close if everything's clear and there are no questions so far. I'll just close the imaging and proceed with the next one.
I actually had a question regarding DICOMs.
Yes.
So I actually previously, not actually in brain MRI, but I had some experience using DICOMs for cardiac MRI, but it's a question in general. In some cases, is it possible that the slice thickness between each files is sometimes uneven? Does it happen in brain MRIs as well? In that case, is it possible to at least convert it to a more uniform imaging? Are there ways to do that?
Yes. This is a great question. Yes. So different sequences. So when you scan the brain, you use different sequences, and sometimes, more often than not, the sequences are obtained in different slice thickness. So how I can represent that? So here, the T1 post contrast imaging, this folder, see how many slices it comprises. 122. These are 192 slices of the brain. And if you open this, we see only 160. And if you open this one, we see 192 as well. And the fourth folder, like the fourth acquisition, it comprises only 40 items. This means 40 slices. So what this tells us, it tells us that different sequences usually come with different slice thickness. And you cannot, this is a common problem in feeding an algorithm with standardized data. You have to make all the sequences, all the slices matching each other in one study, you know. So you can have like when the algorithm is being trained, it's trained on all the 4 sequences, and you cannot properly train the algorithms if the slide thickness is different. Like this is a research area, and it's in the future. I hope that you won't have to match the slices of the different sequences. But for now, one part of the pre-processing of the data, we won't be dealing with that today, but this is why I'm showing you that, and I'm going over why we need to pre-process data. So one important part of the pre-processing is actually matching the different co-registering, this is the right word, co-register the different sequences to one slice thickness. So like plenty of cases in the BraTS dataset have been co-registered to an anatomical atlas. So we get, let's say, these slices, and we are putting them in an already available brain atlas, and so that it's standardized. This is a step that is used to standardize the dimensions of the dataset. Another option, additional one portion of the BraTS dataset has been co-registered to the T1 sequence. So let's say the T1 post-contrast comprises only 1 millimeter thick slices, and let's say the FLAIR imaging is in 5 millimeter slices. So what we need to do before feeding that into the training pipeline is to co-register the FLAIR slices to the T1 post-contrast ones. So it's called co-registration. So yeah, your question is spot on. Different sequences have different thickness, exhibit different thickness of the slices, and for the purposes of the challenge, they need to be co-registered.
Isn't this like the problem that we talked about in the beginning of the session, like the normalization and standardization problem?
Of course.
That's why
Yeah.
That's why we need pre-processing, so we can get all the data same as each other's, so we can get the same results in training tests.
Absolutely right.
Yeah.
At this stage of brain tumor segmentation algorithms and research, this is the common pipeline. We need to standardize everything so that we can produce algorithms with good performance. But the problem is that it comes at a cost. There is some co-registration mismatch that may occur. There's some extrapolation, and sometimes if you load the MRI study into a standardized atlas space, as is the SRI-24 or MNI, it can distort the image, which is not realistic for clinical practice. So yeah, the future a future an area of research is to how to create good performing algorithms on raw data. We're not there yet, but based on the literature that I have read, this is a future area of research. So for now, we are doing the pre-processing, we're standardizing our data, and yeah.
Another small question, just to be curious about, like these scans, like there are, like, I think something called Tesla, like some Tesla value of scanner. So usually, what is the standard MRI scanners that we get images? Like, are there like 1.5 Tesla images? Because in some cases, like there are 3, there are 7. Like, does it also vary between organs? Like, is there a standard version for brain MRI?
Yeah, this is also very variable. As I said earlier in the session, the models are different. In some institutions, 3 Tesla is standard. In some institutions, 1.5 is standard. Usually these are the most common field strengths that are being used. And in order to use, like, for example, 7 Tesla, you need specific indications. Like, for example, for epilepsy, if you want to find a very small cortical dysplasia that is producing the clinical picture of epilepsy, it's better to use 7 Tesla, but those scanners are more expensive and they're not widely available. So again, this is why pre-processing of data is needed to match the differences in the scanners used. So again, it depends really on the region, the country, institutional policy, etc.
I understand. Thank you very much for the explanation.
So I'll continue with the next sequence. Again, we have to wait since it's not paid. So this is another issue with the raw data. As you can see here, the orientation of the slices is different, right? On the previous scan, they were like axial. So there was like, if you see the video, the slices were like that. And on this scan, it's like that. So these are coronal slices. And one part of the pre-processing would be to, since this is a 3D acquisition, to actually convert it to axial plane. So let me just find a slice where it's evident. So here you can see that actually the white matter is a bit grayish and the gray matter is a bit whitish, right? Opposed to the previous image that I loaded. So here the cortex, which is the gray matter, is actually hyper intense. It's whitish, and the white matter is actually grayish. So it's the opposite of the previous case. So this is T2 weighted imaging. In T2 weighted imaging, one thing happens, and is that the fluid is super bright. So like these are the brain ventricles, and they contain fluid. And on T2 weighted imaging, this fluid is super white, super bright. I'll show you in a second. Let me try to. It takes time to load. Okay, it's not that. Just give me a second to show you T2 weighted. Okay, so this is the T2 weighted imaging. Here it's even better. The cortex, the gray matter, is actually whitish. The white matter is grayish. So this, you know that this is T2. And you see the fluid here, it's super bright. And sometimes this is is a bottleneck, you know. If you have a lesion here and you want to, you know, be more precise, all this white signal, all this hyper intense signal is actually preventing the radiologist to have a clear idea of what's going on. And this is why there is a separate sequence, which is the one that I showed in the beginning. It's called FLAIR. It's FLAIR. It's written like that. This is how it's written, fluid attenuated inversion recovery. So based on the name, you can see that it has attenuated the fluid. So here we still have the T2 imaging, but without the fluid. So the hyperintense signal is removed, and it gives us a very clear picture of what's going on around the ventricles and here near the sulci, etc. So now I'm sure that you already can guess whether this is T2 or not, and whether it's FLAIR or not. And I'll load the last sequence. I already loaded it. Is this one. So is this T1 or T2?
I guess it's a T2 or maybe, yeah, maybe T2 because the fluid is not brighter. It's still dark.
So the fluid. Yeah, look at the main let's focus on the main way to distinguish those. As I said, the white matter is whitish, the gray matter is grayish, just like it's an anatomical picture of the brain, basically. So on T1, the fluid is dark. So intrinsically dark on T1. So I'm sorry, we have to wait for 10 more seconds. Maybe the next time, if I'm doing something, if I'm presenting something using Gradient, I should hope pass by my institution to present from there. So, you know, the fluid is dark, is hyperintense on T1 intrinsically. So you don't look at that. You look at how the gray matter is gray and the white matter is white. So this is T1 weighted imaging. And one question I have, is it contrast enhanced or not?
I think not. No, not contrast enhanced.
Great. And why it's not contrast enhanced?
Because I think like the tumor, like usually in enhanced versions, like the tumors have hyper intensity, like slightly lighter. So I think here I cannot see anything like that. So that's why maybe.
Well, so in order to keep it simple and not use how the brain lesion looks, in order to gauge whether it's T1 or T2, let's forget the brain lesion characteristics. Let's just focus on the basics, and which are, you don't see any vessels here. If it's contrast enhanced, you see all the vessels carrying contrast being hyper intense. So you don't see any vessels. So this is pure native. It's called native T1 weighted imaging. And another reason why it's important for you to know that is because sometimes brain tumor segmentation algorithms take a hyperintense vessel and mark it as a metastasis. And this is why you need to know how a vessel looks on a T1 post-contrast enhanced imaging. Let me just open the contrast enhanced imaging. Let me try to do something like that. So as you can see, the brain looks the exact same way, The only difference are the vessels. Here, see on the contrast enhanced, the vessels are actually carrying contrast and hyperintense. And as I said, sometimes the brain tumor segmentation algorithm marks this as a metastasis, and it can lead to erroneous results and low performance. So this is why you need to know that this is one of the mistakes that the brain tumor segmentation makes when segmenting brain tumor algorithms. And how to know whether, for example, this dot here is a metastasis or a vessel. So you just scroll up and down and you see that it's continuous, it moves along the sulci. It moves along the sulcus. So this is not a metastasis, it's just a vessel. So here, if you scroll up and down, again, you see the vessel. Okay, good. And let me open this sequence again. So what's that? T2 or T1?
T2.
T2.
T2, great, excellent. As you know, the white matter looks grayish, the gray matter is whitish, and the fluid, this is T2 weighted. This is not flare. This is just to T2 weighted imaging because the fluid is extra bright.
Extra bright.
And let me open this one. So what sequence is this one?
This flare.
That's
Yeah,
a T2,
exactly.
but it's flare. Yeah.
Flare. T2 flare. Flare is more than enough. So it's basically the T2 signal and the signal from the ventricles and sulci, basically where you have fluid is just removed. And also it's important to know which sequence is what, because if your model, if you run into some problems when training your model, you need to know which parts of the tumor, how the different parts of the tumor look on different sequences. So I won't be, so we have a separate session that will deal with that. It might sound annoying that for several topics I was like, well, we'll talk more about that tomorrow or next week, but you understand that it's a lot of information and we cannot conduct it in one session. I'm just laying out the basics so that you can have the foundation for the next sessions that are to come. So give me a second. I'm sending you a link in the WhatsApp group. So this is basically the next step. Let me share my screen again. So the last time we met, we guided you on how to download the data. I guess all of you, I'm sure that all of you have already downloaded the data. And so let us make a comparison. You already saw the DICOM files and the software that we needed to open them. I will go to a preprocessed BraTS dataset. So here, the cases, you already are aware of how they're named. If you open a case, here we see the ground truth annotation. This is the segmentation, and we see the 4 sequences. The last time I showed you the software that we prefer. Again, you can use 3D Slicer. If everybody is using ITK Snap, we don't have to dive deeper into 3D Slicer, but if you prefer to go over 3D Slicer, we can have a separate session that compares them both. But for now, we stick to ITK Snap, and I would just open the same way we did in the first session. I'll open a nifty file. So here you can see that it's not DICOM, it is .nii file. This is the nifty file. And I'm opening the T1 post contrast. As I said, as I showed you the last time, you can click on this button to visualize the whole, to visualize only this image, so it's more, so it's larger. You can use the right mouse button to zoom in and zoom out. And there is something that should be very eye-striking. I will just open the DICOM file again.
But those ones are a bit blurry than the other ones, I guess.
Yeah, this is, we can put it this way, but let me just show you both images side to side so that we can make a direct comparison. Let me just open the contrast enhanced. Give me a second. Yes, as you mentioned, like it looked a bit blurry, and this is why this is one of the scanner bias that I mentioned in the beginning. Different scanners obtain imaging in different quality. So in order to make an algorithm more reproducible, it's good to feed it with data that is not only high quality, because it will underperform when it's applied to lower quality data. It's good to have a diversity of resolutions. So this is one of the reasons why some scans look blurrier than others. The quality is different. But here you can see that on the nifty file, this exactly this
The fat suppression thing.
no, it's just here you can see only the brain, and here you can see
the skull structure.
Exactly the face, the eyes, the skull structure, everything. So this is an essential part of the pre-processing, skull stripping. We won't have time to go over skull stripping today, but I'm just showing you why we need it and how it actually looks in practice. So the skull stripping, it's a process that removes the skull, basically removes everything and leaves the brain. And when you have the brain, you cannot identify the patient, but as I said earlier, here you can easily reconstruct it, and you can share data that has that can be de-anonymized. So all the BraTS data that you see on the left-hand side of the screen is pre-processed, skill-stripped, and co-registered. So all the different sequences. Let me get back to. So let me open T2 flare as an additional image. So every single slice of this T2 flare imaging corresponds to a single slice of this T1 imaging. They're co-registered. This is an essential step. As we saw earlier, and I can show you now, here we have 40, only 40 scans, and when we have, let's focus on the right-hand side of the screen. If we have a study with 40 slices and a study that captures the exact same area but has 192 slices, it means that one slice from the T1 sequence does not correspond to a single slice from the T2 sequence. Here, when I move to another slice, the gap is very different. A lot is happening here. The ventricles are much smaller, so this is the thickness of the slices is different. Whereas here, when I move to the next slice, the change is very different, very small. So like here we have much larger number of slices. And when we get back to the left-hand side of the screen, this is co-registered pre-processed data. You see that whenever I move the T1 sequence, the T2 sequence moves in the exact same way. So like one slice from one sequence correspond to the exact same plane and exact same coordinates to the other sequence. Okay. I guess this is enough for visual representation and visual demonstration of what pre-processing does. I'll get straight to the link that I shared in the WhatsApp group. It will take you here. MRI CRO-GL. So this is one of the tools that is used to convert DICOM files to Nifty files. I think I forgot to say that the skill stripping tools that we'll be dealing with require the DICOM files to be converted to Nifty. So the next step after setting up the environment, getting yourself acquainted with raw MRI data is to learn how to convert these DICOM files to Nifty files. So I shared the link to this page in the WhatsApp group. So it will take you here, and this is it has a version for Mac, for Linux, for Windows. I have already downloaded the Windows one. So this tool can be used when you download this file and install it. It's a visual interface of this tool. So let me just show you what it looks like. It's microGL, MRI CRO-GL. I open it, and it looks like a software. And in order to get to the point where you convert DICOM to Nifty, you should go here, import, and click convert DICOM to Nifty. So this is how using the software works when you're using the visual interface. Alternatively to that, you can go to, give me a second. You can convert Nifty to DICOM using a code. And if you want to use the code, here is the GitHub page of this tool that we're going to be using, and I'm going to share the link to this page. And it will give you access to the GitHub page, and you already have access to the two versions of this tool that you can use to pre-process raw data. Let me just briefly share my screen for one last time. So here is the tool, and you can set up the output directory. You can select a custom folder where the Nifty files could be saved. So here you can choose the output format, and most of the settings are just default. If you lose yourself in the settings, you can always click reset default. And it's pretty like the process of the conversion is pretty easy. Let me just so this is a folder with one MRI study that comes in DICOM. I just drag it here, and based on the settings, it just converts it to Nifty. Here you can see that it's already being converted to Nifty, bearing the patient name, the study name. So yeah, it's pretty easy to use this tool. There's some specifics when it comes to converting a large data set, and you can depending on the folder structure and how you output name, how your output files want to be named. But since we're already so we won't be getting deeper into this topic for now. It's important to just know what's the tool that is used for converting DICOM to Nifty, how the DICOM looks, how the Nifty looks, how to recognize the sequences, and to just know what happens in the background. So a lot of details are there for pre-processing, and we will continue dealing with the pre-processing in a more comprehensive way tomorrow and the days after. So I will stop presentation here. I think this is enough for you to grasp on. As I said, whoever hasn't installed all the tools that I went over is free to stay with me after the meeting so that we can install them together if you haven't managed to. If you have any questions, feel free to ask them. If you want me to show you more stuff related to recognizing sequences on how as I said, we'll be conducting a separate session related to brain tumor, how different brain tumor looks on MRI, how they look on different sequences. But if you have a question that's right on top of your tongue, you feel free to ask it. And yes, the session is recording. You have access to the recording. Tomorrow's session is going to be held at 12 p.m. Lagos time. So, and is 1 p.m. Central European time. From what I understood, there was some misunderstanding regarding the timing. I used my Windows clock to manage to see the different time zones. So yeah, it's going to be held at 1 p.m. Central European time. This can serve you as a like the time zone which you can refer to when getting on these meetings. I'll send an email with the meeting link, as I said, to avoid any misunderstandings. And yeah, you're ready. The stage is yours. You're free to ask questions. Yeah, there's a question from Magdi.
Yes, so actually the question was like is not directly related to the data itself. Like I actually wanted to ask you about the competition because like I was actually reading a link that you provided previously, which is like MedVision, which was a previous winner's website which has some instructions on how to work on this challenge. So when I was going through that, I saw that like most of the competition winners solutions are actually not that innovative in terms of architecture. So I just was curious, like let's say we are making some models and we are getting good results, but how can we ensure that like our like for example if I write a short paper, like what should I target to ensure that it gets accepted, like just in terms of like reading papers or like just to thinking the strategy. So since I haven't like done it before, so I just wanted to get some advice on it. So like what type of things should I look for if I want to read some papers or if I want to learn some architectures?
Yes. Okay. That's again spot on question. So you know, the whole purpose of this course and the events that follow are to give you the basics, the foundations on how to train a model and submit to the challenge. So you don't have to worry whether your algorithm or paper will be accepted, since our goal here is to help you with the short paper writing and with the creation of the algorithm. So the next session, for example, the next session won't be conducted by me, will be conducted from another colleague, a mentor, that who has been very successful within the BraTS challenge. So he will introduce you to how to fine tune, what to look for when training an algorithm, different architectures and everything. So the point here is for you to have the foundation. So as long as throughout the next week, we will also be giving you the codes for training. And just I'm trying to assure you that no matter how well the algorithm performs, the goal here is to just give you the basics and to reach the point of having a Dockerized, containerized algorithm that you can submit. We'll be assisting with the short paper writing so that you don't have problems with that. So you don't have to worry whether your submission will be accepted or not. Like the goal is to have introduce you to the basics and have everything in place. When it comes to innovative approaches, it's I don't know how to put it. They're great approaches. It's really hard to actually come up with something that's very, very innovative and to actually work well. And especially it's hard to do it in a short period of time. but you can get there once you have the basics. You know, you can't, at least from my personal experience, I don't think one is able to, you know, come up with something extraordinary and winning just like that. There are several steps that you should go through, and it all starts with the foundation. Um, I hope I managed to, assure you that, give you assurance, reassure you, and also, um, uh, yeah, console you in a way that, making something innovative when it comes to brain tumor segmentation models is not something easy, but eventually doable after we have mastered the very basics.
Yeah, I understand. Thank you very much.
Oh, okay. Great. I hope I see you tomorrow. Tomorrow's session will be more technical, since the mentor will have more of a technical background, and he'll dive into more technical details in terms of brain tumor segmentation models tomorrow. And he has, I would like to introduce him in advance. He's called Maruf Adewo. Um, he's from Nigeria, and he has managed, together with Dr. Onozoro, to develop the Brain Tumor Segmentation Challenge Africa. And they have been through a lot of hurdles, and they have managed to overcome them to foster a culture of collecting data from resource limited setting and actually training algorithms. So it's not only that he's very technically proficient in training models, but it also has a fascinating and motivating story on about how he ran from zero to hero. Yeah, several sessions. He'll conduct several sessions, technical sessions, and I hope I see you tomorrow and the day after. I'll be updating you in a timely manner on all the subsequent events. I think the timing, the time that we have uh, chosen is quite good, because it's morning in the US, it's late afternoon in Asia, it's midday in Europe, so everybody can join without having to wake up at 5 or stay late until 1 a.m. Okay, if you come up with a question, feel free to ask in WhatsApp, over email, and yeah, see you tomorrow and the days after. Again, whoever wants to stay for setting up the Python and VS Code and everything is free to do so.
Yeah, see you. Bye bye.
I want to see. I haven't downloaded Python.
Okay, great. Let's do it together. Would you prefer to share your screen, or?
Okay, let me share.